Hello, everyone. Welcome to the April 15th edition of Calc 2. Today, we're going to be talking more about conic sections, ellipses, and hyperbola. So, reminder, you have a web assignment due on Friday. It's just over section 10.1. So today, we're going to learn about section 10.1 continued. So we started 10.1 last time. We're going to finish it today. All right, so remember last time we introduced the ellipse, and so today we're going to talk about some properties of the ellipses before we move on to hyperbola. So the first thing you should know is that the ellipse actually has the same reflective property or a similar reflective property to the parabola. If you connect the line from a point P to each of the two foci, they make equal angles with the tangent line at P. This is another good fact that you should ask Dr. Glenn to prove for you in the fall semester, because it will be much easier with a knowledge of vectors than it is with what we have right now. So by now you probably know that some ellipses are close to circles, much like the planet's motion around the sun, and others are very oblong. One reason that astronomers had difficulty detecting the orbits of planets, the fact that they were ellipses, is because the foci of the planetary orbits are relatively close to the center of the sun, making the orbits nearly circular. To measure how the ovalness, so to speak, of the ellipse, you use a ratio called the eccentricity. So the eccentricity E of an ellipse is given by the ratio E equals C over A, where C and A are the same as before. C is the square root of A squared minus B squared, and A is the half the length of the semi-major axis. So let's take a look at a picture of what this looks like. So when C over A is very small, that is close to 0, your ellipse looks very close to being a circle. But when C over A is very close to 1, like it was in the example of the ellipse I worked in class previously, it is very stretched out, looks very oval-like. One thing we should do before we move on to hyperbola is find the area of an ellipse. All right, so let's solve for y. And there'll be two of them. It'll be plus or minus the square root of, let's see, b squared minus b squared x squared over a squared. Or if we want to simplify, we're going to get b over a square root of a squared minus x squared. So if I look at an ellipse, it'll look something like this. This is the positive square root, and this is the negative square root. That means that the area should be equal to 2 times the integral from negative a to a of this b over a times the square root of a squared minus x squared. So how could we find such an integral? Well, we need to use trig substitution, where x is a times the sine of theta, and dx is a cosine of theta d theta. We substitute this in. One can check that the integration bounds from this substitution will become negative pi over 2 and pi over 2. We see that these a's cancel out. We get ab cosine squared of theta d theta. All right, and this will equal 2ab, integral from negative pi over 2 to pi over 2. And remember, the cosine squared is 1/2 plus the cosine of 2 theta over 2. We integrate this. We get 1/2 theta plus sine of 2 theta over 4, where we plug in negative pi over 2 and pi over 2. And what we should get is pi over 4 plus the sine of pi, which is 0, minus negative pi over 4 plus 0, because the sine of negative pi is 0. And so we get 2ab times pi over 2 is pi ab. So the area of a ellipse is the product of half the length of the semi-major times half the length of the semi-minor axis, times pi. The circumference of an ellipse is much more complicated. We're going to ignore that. But the circumference of an ellipse cannot be calculated through nice functions. The integrals just cannot be done. All right. So let's switch to the last of the conic sections that we're going to talk about, and that's the hyperbola. So remember, for an ellipse, the sum of the distances between the foci and a point on the ellipse is fixed. But for a hyperbola, the absolute value of the difference between the distances from a point y to each of the two foci is fixed. So for the ellipse, you added the distances to the two foci, and that sum was a constant. Now you take the difference of the distances to the two foci, and that difference, the absolute value of it, must be fixed. So a hyperbola is the set of points xy for which the absolute value of the difference between the distances to two distinct fixed points, which we call foci, is constant. All right. The line segment through the foci intersects a hyperbola at 2 points called vertices. The line segment connecting the vertices is called the transverse axis. And the midpoint of the transverse axis is called the center. All right. So a hyperbola has two distinct branches. So let's take a look and see what they look like. So this picture shows us much of the hyperbola. We see that the distance from our point xy to one focus minus the distance from the point xy to the other focus is a constant. And the center is halfway between the two vertices. The line that goes between them is the transverse axis. All right, so let's go back to the initial screen. And let's give you the standard form of a hyperbola. The standard form of the equation of a hyperbola with center HK is x minus h squared over a squared, y minus k squared over b squared equals 1, where that's if the transverse axis is horizontal, and you get a different equation if the transverse axis is vertical. The vertices are a units from the center and the foci are c units from the center, where c squared is a squared plus b squared. Graphing a hyperbola takes a little work, and it's helpful to be able to graph its asymptotes. So a hyperbola has two asymptotes. The asymptotes pass through the vertices of a rectangle of dimension 2a by 2b with center HK. The line segment of length 2b that connects the point HK plus b to HK minus b is referred to as the conjugate axis. For a hyperbola that's opens up horizontally. So we'll take a look at this. So we see here how we draw this box. The box opens up from the center all the way to, and the sides go all the way to hit the vertices. and they go up and down until it's b units above and below the center. So you can see what the two asymptotes are, and from this we can easily figure out what the equation for the asymptote should be. So what this tells us is, for a horizontal transverse axis, the equations of the asymptotes are y equals k plus b over a times x minus h, and y equals k minus b over a x minus h. For a vertical transverse axis, the equations of the asymptotes are y equals k plus a over b x minus h, and y equals k minus a over b x minus h. And last but not least, the eccentricity e of a hyperbola is c over a. All right, so let's do an example where we find all of these things. So let's look at the equation of the hyperbola x squared over 25 minus y squared over over 16 is 1. We see that a is 5, b is 4, so c squared is 5 squared plus 4 squared. I think that's 41. So c is root 41. Pretty clearly, the center is 0, 0. So the vertices are a units from the center. So that's 5, 0, and minus 5, 0 are the vertices. The foci are c units from the center. So that's root 41, comma 0, and negative root 41, comma 0. And the eccentricity is c over a, which is root 41 over 5. We also need to know what the asymptotes are. So we know that h equals 0, k equals 0, a equals 5, b equals 4. So that tells us that the asymptotes are y equals 4/5 x and y equals negative 4/5 x. All right, so now we can graph all this stuff using Desmos to help us out. Okay, so the center was at 0, 0. We have the vertices at 5, 0 and negative 5, 0. We have the foci. And we have the asymptotes. Now it's time to graph the hyperbola. X squared over 25 minus y squared over 16 equals 1. All right. And so we have all of these things that we wanted to see. We have the two asymptotes, we have our hyperbola in black, and we have the vertices and the two foci. So I want to show you one last thing about hyperbola before I give you an example. So the last thing is, what does the eccentricity tell us? So the eccentricity is bigger than 1. So if it's close to 1, you have very flat hyperbola, as seen on the right. And if the eccentricity is very large, then you see that the hyperbola explodes very quickly. And so the two sides of the hyperbola get big very fast. And that's the main thing to know about the hyperbola and how it relates to the eccentricity. All right, last but not least, it's time for you to have an example. So it's an example for you to complete. So I want you to find the center, the foci, vertices, and the eccentricity of this hyperbola. Note that it is a vertically opening hyperbola. And sketch the graph. You're going to need the asymptotes, so I'll add that in there too. Let me know if you have any questions, and I hope you have a good day.